Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. You can subscribe to our show on iTunes, Stitcher, TuneIn Radio, or add our RSS feed to your podcatcher. You can also follow us on Twitter or Google+, and please give us feedback. Leave us a review on iTunes, send us a tweet, send us an email, leave a message on Google+, or leave a comment on our show notes. Leaving a review on iTunes helps other people find the show so that they can enjoy it as much as you do. I'd like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. For details on how to support the show, you can visit our site at pythonpodcast.com. I would also like to thank Hired, a job marketplace for developers, for sponsoring this episode of Podcast.init. Use the link hired.com/podcastinit to double your signing bonus. Linode is sponsoring us this week as well. You can check them out at linode.com/podcastinit and get a $10 credit to try out their fast and reliable Linux virtual servers for your next project. We are recording today on November 17th, 2015, and your hosts as usual are Tobias Macy and Chris Patty. Today we are interviewing Stuart Mumford about SunPy. Stuart, could you introduce yourself, please?
Hi, I have just finished writing up my PhD on numerical solar physics at University of Sheffield in the UK, and for the last couple of years I've also been the lead developer of the SunPy project.
So Stuart, how did you get into programming in Python in particular?
My first kind of formal introduction to programming was a Fortran 90 course in my physics undergrad. I had a few modules during my undergraduate on Fortran programming. Sometime late in my second year of my degree, my lab partner introduced me to Python. We taught ourselves it by doing all our data reduction for our third year lab experiments in Python. And by the end of my third year, I had a relatively good handle on scientific Python programming.
And can you explain what the research and applications of solar physics are and how SunPy facilitates those activities?
So the part of solar physics that I mainly am involved with and SunPy kind of relates to is the part of solar physics that studies the interaction of the sun and the earth, specifically all of the dramatic events that affect the earth in one way or another, be it potential to knock out satellites or power grids, kind of the large space weather events are all kind of originate in the outer layers of the solar atmosphere. And the main focus of most solar physics research is the heating of the solar atmosphere, especially the outer layers of the solar atmosphere, heated to millions of degrees, and the precise mechanism of how that energy is transported up into the solar atmosphere isn't known. And sort of the application of most solar physics would be that by studying this heating, we would have a better handle on the physics of what causes these events that cause space weather and their cause effects on Earth. SunPy is a library that is designed to represent and allow scientists to process observational data of the sun. So be it images, spectral data, or time series information.
Can that data also be applied for research in terms of solar renewables, like solar electricity or solar heat?
Maybe a little bit, but not really. Most of the solar side of that, to my knowledge, is about how much radiance of the sun lands on certain places and stuff, and that's not. It's more kind of direct. SunPy is more direct observational data.
And what is the relation between solar physics and astrophysics? Are there any differences in the problem domains or the ways that the research is conducted?
So there are an awful lot of similarities between solar physics and night side astronomy or dark side astronomy. Solar physics, solar astronomy is really a subset. At sort of a basic level, they do very similar things. Like they're both observing space through a telescope onto a CCD. You capture light and form an image, and then have to worry about coordinate systems or transformations of kind of distortions through your telescope or the atmosphere. there's an awful lot of similarities. There are a lot of differences as well, especially around sort of the atmospheric effects are different because you're not observing point sources in solar physics, and you end up with an awful lot more light because you're observing something that's much closer.
It's very interesting. It's definitely a fascinating area of research, and one that I would like to be able to spend more time on, given actually having some free time available. So what was your inspiration for the SunPy project, and what are you using it for in your research?
So I only got involved with SunPy just after its first 0.1 release. I actually saw the release announcement for SunPy 0.1 on Twitter on my way into work, and got very excited, thinking, oh, someone started writing that thing that I've always said I was going to do when I had a free year. And I got into the office and logged into the IRC channel and managed to worm my way into leading the whole project. SunPy, the motivation for SunPy is to provide a more modern toolset for solar physicists. An awful lot of solar physics at the moment uses a proprietary language called IDL, which has some rather major flaws, but it's also it's obviously very useful for solar physics because there's a massive collection of code called SolarSoft, which is really a collection of the last kind of 10, 15 years worth of primarily space-based instrument pipelines. There's about 4 million lines of IDL code in the SolarSoft package. The purpose of SunPy is to provide the sort of core tools that exist in that library, not the instrument calibration routines, which were written by the people that built the instruments. SunPy, the goal of SunPy is to provide a modern Python-based way of representing calibrated solar data for people to work on and do scientific study with.
So can you tell us what SunPy's map and light curve classes are and how they might be used?
So SunPy provides 3 core sort of data types. Map for currently 2D image data, light curve for time series, which is based on the excellent Pandas library, and a spectra class for holding spectra data and data which is wavelength and time. The idea of these is that they provide the base framework for all the other code to kind of work with. There are quite a few different, like SunPy provides access to lots of different instruments, lots of different data sources. And the idea of these data types is that they kind of provide a unified interface to a wide variety of different data sources and instrument types. So the one I've done the most work on is the map class, which is currently limited to 2-dimensional data, or collections thereof. And the functionality it provides is primarily a way of holding the NumPy array, which is the image, and all of the metadata that comes with that image from wherever that source is. I mean, normally it's in a format called fits, and we read that fits file and extract a NumPy array and a dictionary, basically, which is the data and the metadata. Then the map class provides a standard interface to those two things that account for some instruments have, say, the name of the instrument with a key in the dictionary of instrument, and some of them have truncated it to instrument. So you can access the instrument by doing map.instrument, he says off the top of his head, hoping that's right. And it doesn't matter how that information arrived to you in the file. So if you've written a code for one instrument and you've accessed the name of the instrument and the size of the array in physical units, you can swap that out for a different instrument's data and your code will still work fine. The other main thing that map does is deal with providing transformations from array coordinates, so array indexes, to physical coordinates. So there are 2 or 3 solar coordinates, solar coordinate systems that represent points on the sun, be it points on an image on the sun or 3D based around the center of the sun coordinates. What map does is convert from the array indexes to the helioprojective coordinate system, which is measured in like angular distance from the center of the solar disk, and that primarily uses AstroPy to do that transformation. But what map does is make sure the transformation works exactly the same way for all the different sources.
So you were mentioning how SunPy is a sort of Python implementation of some of the capabilities found in the IDL library, and I'm wondering if there are any issues in terms of intellectual property or patented algorithms that you have to sort of steer around in the process of writing and maintaining SunPy.
So the IDL library isn't licensed at all. There's no license on it. It's just made available, which makes it a very sort of grey area, but it is put out there with the intention of being able to use it. But primarily what SunPy has done at the moment, for the most part, is implement similar functionality but in a completely different way, because we wanted to implement Pythonics type functionality rather than just like translating function X from IDL to Python. Mm-hmm. So we've mostly avoided that by not doing it so far.
And you were also talking about, particularly in relation to the map type, being able to do processing on images from the sun. And I'm wondering if there's any computer vision routines that are implemented or available for being able to do automatic feature extraction for certain research purposes.
I've done a bit of work on that personally, but none of it's ever made it into SunPy. For the kind of image manipulation stuff that we do in SunPy, which is mainly rotate and also some kind of transformations to, although this one's not in SunPy yet, but being worked on, is transformations on to compensate for the rotation of the sun, which changes depending on how far away you are from the equator. So the equator rotates faster than the poles. So if you have an image or a time series of images and you want to like rewind or fast forward the image, you need to do some complex warping of the image. And all of these kind of things, we've just been using scikit-image, which is an excellent Python-based image processing library, rather than writing stuff from scratch.
Are there any considerations that you need to be aware of when writing software libraries for practitioners of the hard sciences that would be different if the target audience were software engineers?
So pretty much my entire programming experience has either been writing software as a scientist or for other scientists. But I think most of the considerations for scientific software are in the sort of the way it's developed. Scientific software is pretty unstructured in the way it's normally developed, unless you're talking about developing for a specific instrument, like a calibration routine for a telescope or something. Most sort of software written by academics is sort of, I need to solve this problem, and they'll write something sort of like, basically scientific software never gets out of prototyping phase. Because as soon as you have a working prototype, it's done. It works. It's done the job. So it's kind of from the building a library like SunPy perspective, you have to consider the fact that you have to make it general enough that everybody can use it, and it won't place restrictions on what people want to do, but at the same time sort of encourage people to do things well and use best practices, which is one of the reasons why I think Python is such a great language for scientists. Because for a start, it forces them to indent their code, which to a lot of computer scientists is like, well, you always indent your code. I mean, why would you not indent your code? But I've had people, especially in my undergrad, who would write code with no indentation or spaces at all. It runs fine until it doesn't, and it's really difficult to debug. But it's Python itself makes an excellent foundation, and he's really starting to gain traction within astronomy a lot, and also now slowly but surely solar physics.
So it's really interesting. Within my organization, actually, there's been a little bit of pushback against Python recently because of the fact that it's a dynamically typed language. Some of our architects want us to use strongly statically typed languages instead. But it's kind of interesting hearing you say that Python makes kind of an ideal language for scientists because it enforces some of these best practices like good indentation and the like. Do you find that lots of people writing software for the sciences have discipline around writing tests for your code as well?
No, not in general in academia. Testing, version control, these kind of things are still relatively rare. There's a lot of effort in like excellent projects like software carpentry and similar kind of educational exercises which are trying to teach academics sort of software engineering skills, because mostly academics kind of hit postgraduate research and they may have been taught how to program. Like for instance, my undergraduate programming module was about numerical methods, like solving differential equations numerically, and we had an exercise where we had to, or where I was calculating like orbital dynamics, like three-body problem kind of numerically, but not a lot of effort is, or has been at least, put into teaching scientists how to write code well rather than just how to program.
So can SunPy consume data directly from telescopes and other observational apparatus?
I've never heard of anyone do like live telescope output with SunPy. Your question did make me wonder. It would probably be possible. If I ever get a telescope, I might try it. But the kind of focus of SunPy is science quality, like calibrated data. So when you put a camera at the back of a telescope, you take an image, say we're taking pictures at like 30 frames a second. Each one of those images is going to be relatively low quality because of, if you're a ground-based telescope, atmospheric distortion. You've got a fair bit of air to get through before you reach the sun. And then you've also got like parts of the CCD that are more sensitive than others, or parts of the like certain wavelengths that don't filter properly. You've got a lot of calibration to do from raw camera at the back of the telescope to data that's science quality. And SunPy currently doesn't do any of that, mainly because those kind of routines are written by the teams that design and build the telescopes, because they're the ones that can test the code, like calibrate it with the actual telescope and know all the ins and outs of the telescope design. So we do get a few feature requests every now and then, like, oh, can you support calibrating this, that, or the other? And we're like, we don't have the expertise, or definitely don't have the developer time to port that code or rewrite it.
So basically, it sounds like SunPy is a module in that, like you say, another team would produce the data with their telescope, and they have their own whole code base, and they would hand you the nicely calibrated, well-groomed data sets that you would then operate on with SunPy.
Yeah, that's the idea. And more and more, as the quantity of data gets bigger and bigger. Like, for instance, NASA's most recent flagship solar mission, the Solar Dynamics Observatory, downloads about a terabyte, 1.2 terabytes of data a day. When that was launched, I was still doing my undergrad, and I was looking at the specs of the satellite, and I was most distressed to realize that it could download data from space faster than I could download data on my home broadband connection. And so as that data sets get bigger and bigger, it becomes more and more impractical for people to, like scientists, to do that calibration themselves. So most of the data from SDO is shipped to people pre-calibrated with full coordinate information in the metadata. And that's the kind of stuff that SunPy really works with.
That's really interesting, because hearing one of the other podcasts in the Python space, Talk Python to Me, recently did an episode where they interviewed one of the researchers from the CERN Super Collider, and they were talking about how there was such a really substantial chunk of their software and even hardware stack that was dedicated to that whole process of, filtering the reams and reams and reams and reams of data that these collectors would grab, down to a level where scientists could even begin to actively make use of it. So it's very interesting that for solar astronomy, that's a completely different bailiwick. You folks don't even handle that.
That's the way it's going. It's going more to like that being done as a service to the scientist. But there is still a lot of individual data reduction that solar physicists do for older data or different sources, or current ground-based telescopes mostly ship the raw data.
So I noticed on the project site that SunPy leverages AstroPy internally. Can you describe the relationship between the two projects and why someone might want to use SunPy in place of or in addition to AstroPy?
So AstroPy is a fantastic and substantially larger project than SunPy at the moment. And it's a core library for astronomy. It provides a lot of the functionality that SunPy relies on, whereas SunPy is a core library for solar astronomy, which is kind of a subset. So you could do solar physics data analysis using just AstroPy, because it provides you the tools you need to read the files, and then you would get a NumPy array and a dictionary, and you could do your analysis. SunPy provides sort of wrappers on top of that, like map I was talking about earlier, and also more specific solar related things like constants and calculations for coordinate systems and stuff. Since I've been involved with SunPy development heavily, I've been trying to work closer with AstroPy and sort of integrate these two communities a bit more. This is really the most obvious example of this is probably the most recent AstroPy coordinates framework. It was released in AstroPy 0.4, I think, which is a generic framework for holding astrophysical coordinates, like points in 2D or 3D space, related to some kind of origin, be it the Earth, the Sun, or something. And so, myself and the SunPy community contributed to the design and then the development of the AstroPy coordinates framework. And because of that, we have a nearly finished set of solar physics coordinate frames that use the AstroPy framework. And because we helped design and develop it, it ticked most of the boxes we needed. There was only a few things that we had to add or tweak, like kind of pull requests afterwards, things we didn't think of. And we've had, there's a lot of other kind of problems that we've solved in SunPy, or things we've come up against that either AstroPy have made easier or we have contributed functions to AstroPy. As of the most recent SunPy release, we have used AstroPy units everywhere throughout our code. AstroPy units is potentially the best single submodule in AstroPy and shouldn't really be in AstroPy at all, because it's a generic physical units package. So you take a NumPy array and you can say my NumPy array multiplied by units.meters, and now your NumPy array is a quantity with the units meters. So if you try to subtract an array which was quantity time from your array of quantity meters, it would go, what on earth do you mean you can't subtract a second from a meter? Doesn't make any sense. And raise an error. Like the main way we've used this in SunPy is to simplify our API. So like places before we had like flags for is this in physical coordinates or pixel coordinates, and now we just read the units attribute of the array that's passed in.
Yeah, we interviewed one of the core developers of AstroPy a couple of weeks ago, and the units module, when we were talking to him, definitely sounded like a very interesting and promising piece of software that could, as you said, be broadly useful even outside of the AstroPy or the SunPy packages for anything that has to do with physical quantities.
That's cool. Who did you interview?
Eric, and his last name is escaping me.
Tolerud.
Yes.
Yes. Oh, very nice. He's the guy that wrote or leaded the coordinates development. The other thing that we've that's come out of me being involved in the AstroPy community is the Pythian Astronomy conference, which is brought together different people from different fields and projects, but all people who are working with Python and doing astronomy or astrophysics. And we had a really good conference last year in April, and there's another one coming up in March, and they've been really constructive of that one.
And so looking at the documentation, I got the impression that there's a fair amount of visual representation of the data for analysis. Can you describe some of the challenges that has posed, and is there any integrated support for Project Jupyter or any other graphical environments that SunPy supports?
So most of the SunPy visualization routines have used Matplotlib. So if you create a SunPy plot in a Jupyter notebook, it behaves as you would expect it to. One of the more recent changes to SunPy's plotting is the fantastic WCS axis package, which has been the development of has been led by Tom Robitaille, who's one of the core AstroPy devs. And WCS axis is a package that allows you to do like kind of 2D image plots, but other 2D plots in Matplotlib, and have your coordinate axes, your coordinate frame, and your axes not aligned with the array. So you could imagine having your square array and your physical coordinate system rotated 45 degrees. And when you create a plot with WCS axes, all of the like image coordinate grids and the ticks around the edge of the frames would all be aligned to the physical axis, like 45 degrees to the around the edge on the edge of the Matplotlib plot, and allows you to do like mouse over and overlays and stuff in different transformations. And that's made a big difference to the map visualization routines. The only other kind of visualization stuff that SunPy's had some involvement with is the Ginga project, which is a graphical tool for viewing FITS files. And we've done a bit of work to improve the solar physics support in Ginga.
So what are some of the most interesting applications that SunPy has been used for?
I don't have a lot of specifics. I mean, I know a few research projects that have used SunPy. One of my colleagues has done some work studying waves in the solar chromosphere, and he used SunPy and Python for a lot of that. Another one of my friends has built our Matplotlib like kind of graphical tool where he could click on the images to measure how features of the solar limb changed with time and record those. I think one of the most interesting, albeit currently hypothetical, uses for SunPy is the new DKIS telescope that's being built on Hawaii. It's going to be by quite a margin, the largest solar physics telescope that's ever been built. And we're currently discussing with that project about how they're going to use Python and hopefully also SunPy.
And so before we move to the picks, are there any other questions that we should have asked but didn't, or anything else that you'd like to bring up?
Not that I can think of.
All right, with that, we will move to the picks. And for my first pick today, I'm going to pick the Elm language, which is a functional language that compiles to JavaScript. And one of the things that it says on the homepage for it is that if you can successfully compile it, then it's guaranteed to not have any runtime exceptions, which is quite a bold claim. And everything I've been hearing about it is very positive. And I'm actually planning on using it for a project that I'm going to be starting fairly soon. So definitely recommend checking that out. Just seems like a really interesting and useful way to do front-end development. My next pick is the Avro serialization specification. And what makes this interesting is that it is a binary format, and it also keeps the schema of the data co-located with the data itself. So the actual serialized form of the message includes the data schema, so you can actually change the schema of your data over time, but you will still always be able to read the data that's been serialized because of that co-location, the locality of the data. So I've been considering using that for another upcoming project that I'm going to be doing soon at work. Definitely seems like one of the most flexible serialization schemas that's available in terms of being able to actually maintain the semantics of the data along with the data itself. And for my last pick, I'm going to choose a website called Common Sense Media, and it is a site that will give you useful reviews and summaries of various media, whether it's movies, video games, books, and it's a good way for parents to be able to check up on a movie or game that they're considering letting their kids watch or play without having to actually watch the entire thing beforehand and just get a good overview of, what's the level of violence or profanity, and, is this something that I actually want to expose my kids to before you go out and purchase it. And with that, I will pass it to you, Chris.
Thanks, Tobias. My first pick is a website. It is called MassDrop, and I will say that if you are in any of these sort of groups that MassDrop panders to, this thing is dangerous. The basic idea is that they will have agreed upon drops. There are different subject areas, like there's one for keyboards, there's one for keyboards and input, there's one for personal carry, so it can be anything from wallets to small tools or whatever the case may be. There's one for hobby, so it has things like drones, or like they just recently sold a set of lock picks and a practice lock, so you could learn lock picking. It's basically, and the idea is that if you get in on a drop, then the more people who join the drop, the lower the price of the item becomes to within a certain threshold. And it's a really neat way to A, save some money on some interesting things, and B, find out about some interesting things that you may never have heard about. The wallet that I bought, my Ridge wallet, I found out about and bought through MassDrop that I picked in the previous episode. It's a great site. People have pointed out that you don't always necessarily save a ton of money through MassDrop, but It's never, you never end up overpaying. I'll say that much. And I have definitely provably found instances where I've saved a fair bit by using it. My next pick is a beer called 21st Amendment Fireside Chat. This is an interesting one. It is a spiced English ale, and it is a winter beer. Very smooth, very tasty. It's just a really good, solid winter ale with very little hop signature, nice and malty. And my last pick is a YouTube show that's kind of an interesting sort of mishmash. It's called Extra Credits, and it was originally meant to discuss games and the games industry, video games rather, the video game industry and video game design. But through this sort of sideways, I don't want to say accident isn't quite the word, they ended up going in depth about this one particular game that was set in a particular period in history, and they had such huge crowd response to that they now have this side series where they go through and discuss various events and periods in history, nothing to do with gaming. It's kind of like, so it's like video games, video game design, and history. It's an interesting show, definitely worth a look. So Stuart, what kind of picks do you have for us?
I have a few. A few weeks ago, I think one of you picked out "You Are Listening To" as the background noise thing.
That would be me. Love it.
Yes, I went on that and went, oh, that's interesting, but it needs more space. So I discovered that there is a live stream from the International Space Station that includes the ground to Earth radio as an audio track. So for the last few weeks, I've had that running in the background. I also, a little while after that, discovered that there is a high definition video feed from some cameras that was recently attached to the outside of the International Space Station. And that streams live 720p HD video of the Earth, which is just beautiful to have on in the background. My next pick is the YT project, which I thought I would pick out specifically. It's a Python project that I used extensively during my PhD research, which has been mostly numerics based. And it has ability to read in sort of numerical data sets and do visualizations, specifically like slices through 3D domains. The YT SliceBot interface is one of the nicest bits of Python code I've ever had the pleasure to use. And thirdly, a project that I discovered this week is called Calf Studio Gear, which is a set of live audio processing plugins that run on the Jack audio server. I think it's Linux only, but it allows me to process the sound coming out of my microphone with things like an equalizer and a gate and a compressor, and pipe them back out to Pulse Audio and then through to Skype or Mumble or any of the other places I want to send them.
Very cool. For what it's worth, I don't know about Calf because I've never actually used this particular thing, but I know for a fact that Jack runs on OS X as well.
Yeah, Jack does. I don't know about Calf. I think Calf is Linux only, whereas Jack isn't. But Jack is also awesome.
Gotcha.
All right. Well, we really appreciate you taking the time to join us and tell us all about SunPy. For anybody who wants to keep in touch with you and follow what you're up to in the SunPy project, what would be the best way for them to do that?
Well, I have Twitter. My personal Twitter is at Stuart Mumford, and the project is at SunPy Project. There is also the SunPy website, sunpy.org. The GitHub page, github.com/SunPy, and also our IRC channel on Freenode /SunPy, which is a good place to come if you want to have a chat with me.
Great. Well, we really appreciate you taking the time out of your evening to join us, and I'm sure that our audience will enjoy learning more about solar physics and SunPy.
Thank you very much.
Great. Thank you. Have a good evening.
Thank you.